And Steve, the floor is all yours.
Great, thanks, Gerald. So again, my name is Stephen Madden. I'm a geotech engineer with the Vermont Agency of Transportation, and I'll be presenting along with Melissa Landon from WSP Golder. We're going to be discussing this bridge replacement project and interchange design in Colchester, Vermont, where CPT was used in addition to more traditional sampling methods to aid in the subsurface investigation and ultimately the design. So to start with, just to give a brief background on VTrans's use and experience with CPT. We've generally used CPTU on various projects where subsurface conditions are characterized by deep soft clays and loose sands and silts. And these applications are mostly including bridge projects with deep pile foundations or abutment and MSE wall designs where slope stability, bearing resistance, settlement, and seismic site class designations in soft soils were integral considerations to the design. Now in most cases, CPTU has been performed during a secondary site investigation phase to supplement findings from an initial investigation phase, which would generally include traditional drilling, so SPT sampling, drive and watch borings, auger borings, and bedrock coring as needed. And then CPT would be advanced during final design under a secondary mobilization to reduce risk during design and to lower construction costs if the initial findings indicated that CPT testing would be warranted. And so for this project that we're talking about, it's located on I-89 and US Route 2 in Colchester. And for this project, CPTU was used as part of the preliminary investigation. So the project itself is located in the northwest corner of the state. And looking at the image here, we have Interstate I-89, the southbound barrel on the bottom left, and the northbound barrel bottom right, running into and out of the screen, and US Route 2, the bridge carried over the top. And looking at the structure itself, this is from the 1960s, and it's starting to show its age. So the concrete is deteriorating at the piers here, the girders and the beams, again, deteriorating. So a good candidate for bridge replacement. The bridge itself, as mentioned, from the 1960s, and the plans and boring logs from the original construction were available for review and indicated that deep pile foundations were advanced here through soft glacially derived clay deposits, and the bedrock elevation varied significantly from west to east. And with that information, we decided that CPTU and SCPTU were going to be incorporated into the original site investigation program based on our understanding of those site conditions and following review of that historic information. And so looking at a plan view of the site here, again, Interstate I-89 running top to bottom and Route 2 running left to right, with US Route 7 also running top to bottom on the right-hand side. So the proposed bridge replacement was going to be a two-span integral abutment bridge with MSE walls at the abutments and a central pier constructed immediately to the north of the existing US 2 bridge. So the yellow star there indicates the location of the proposed structure, so offset slightly to the north with a realignment of Route 2. In the northwest quadrant, the red star showing the off-ramp from the southbound barrel of the interstate. The blue star showing the reconfiguration that's proposed for the northbound off and on ramps. The purple showing, again, the realignment of US Route 2 and reconfiguration of the intersections with I-89 and US 7. And the green star is showing, again, where US 2 is being realigned, necessitating tall embankment fills and MSE wall construction. Again, another look at the plan sheet here showing the plan view of the proposed reconstruction. So the existing bridge to the south and a realignment to the north. So the yellow stars again showing the location of the proposed abutments and central pier. The MSE walls in blue on 3 sides at each abutment. And again, the green stars showing the location of the embankment fills that would be placed. And so just to touch on the site geology, I'll touch on the overall geology of Vermont, and then Melissa can take over and talk about the specific geology at this site. But in general, in Vermont, we anticipate on any given investigation running into a lot of glacial till over bedrock generally for deep foundations. So till would consist of sand and gravels, generally with refusal conditions on an SPT sampler, and lots of cobbles and boulders generally over the bedrock, so not conducive to CPT testing typically. But for this project, as I mentioned, is located in the northwest section of the state, where we do oftentimes encounter clay deposits given the proximity to Lake Champlain on the western border. And in reviewing the historic bridge plans and the geologic map for this project, that proved to be the case. So I will hand over to Melissa, and she can talk about the specific site geology and the CPT testing that was done as part of this investigation.
Thanks, Steve. So to stay on this slide, a little more detail about the site geology. From the bedrock surface up, we were expecting a dolostone. We were expecting the glacial till. And our understanding is that we would find thinly laminated varved silting clays that were formed in glacial Lake Champlain during the Laurentian ice sheet retreat. And then above that, massive silt and clay deposits formed by a glacial ice dam failure when the Champlain Sea inundated the valley. And then above that, we would have some fine sands deposited by the Lamoille River channels. Like these are historic. And so that would be alluvium. And so we took this into consideration when we were planning our subsurface investigations. Steve, can you advance? And so what you'll see here in this image is the center line of the existing US2. And you'll notice there are several locations where there are borings, and then there are several locations where there's CPTs, or in this case, seismic piezocone and then piezocone tests. And on my screen, I'm seeing the slide is a little bit jumbled, so I'll do my best. So our ultimate goal is to characterize the soils for approaches and the embankments and the bridge abutments and the pier, mostly focus on the design of those major components of infrastructure. We performed 15 conventional borings to refusal. We performed 6 conventional borings with 10 feet of rock core per VTrans specifications. Anywhere where there would be piles driven to bedrock, we're required to collect 10 feet of rock core and characterize that as the basis for where the piles will sit. And in these conventional borings, we perform standard penetration testing, mostly for any alluvium and the higher strength clays, and then we perform field vein shear testing to characterize the lower strength clays. We also collected a number of hydraulic fixed piston samples using the Gus sampler and these were Shelby tubes for advanced lab testing. And then we performed 4 seismic piezocone tests and 2 regular piezocone tests. And we did this from a truck-mounted drill rig. So it's typical for us to try to minimize the expense associated with mobilizing a full CPT rig, particularly since a lot of these locations where we perform CPT were off-road. And so we used a conventional track-mounted drill rig. And on the site, we had actually 2 drill rigs. We operated for a total of 18 days to collect to perform the necessary borings. With 2 of those days, with one drill rig for the CPT. And as I noted, the conventional drill rigs are preferred as a cost savings mechanism and where we can continue to keep the drill rig on site to perform the additional borings when CPT is completed. Next slide. We then progressed the subsurface investigation into the characterization of the laboratory characterization of the samples, as well as looking at the cone penetration test data. So we sent our SPT samples away for index and classification testing, and then we sent our Shelby tube samples to the lab. And the first thing that we typically do is perform X-rays on the Shelby tube samples. And this is to allow us to find any sorts of senses of disturbance or cracks, voids, and inclusions so that we can avoid either specific parts of the tube or the entire tube, as to not waste money on further characterization of disturbed soil. Once we got the results back from the lab of one of the X-rays for boring 110, which is nearby the eastern abutment, you'll notice that we did, for this deeper tube, pick up those varves that we expected, confirming the geology. And we also found some shadows and inclusions. And so when we were planning the lab testing, which consisted of one-dimensional constant rate of strain consolidation, incremental load consolidation, and triaxial shear and compression, we were sure to select specific locations to avoid any of the disturbance that we did find, although there was limited. Following receipt of the lab sample data, we then set to create a site-specific set of correlations for our CPT, specifically focusing on the clays for undrained shear strength and for preconsolidation pressure and overconsolidation ratio. We also reviewed the CPT data, specifically the shear wave velocity data, and set to work on establishing the seismic site classification. And also, we used the shear wave velocity for secant modulus determination for subsequent settlement modeling. And we also used not just the lab data, but the field vein data to correlate to the CPT. Next slide. And so one of the important things that the CPT did for us was allow us to better develop our stratigraphy and the engineering properties for the soils, particularly understanding that there's variability in the bedrock surface, which we encountered, which you'll see in the next slide when we advance. And then also any variability in the engineering properties specific to our need to evaluate each abutment and pier separately, and either the east and the west embankments separately. And so you'll see here, this is a close-up of the location near the proposed new bridge to the north. And so we've got the six conventional borings, and these were drilled specifically in those locations because of the requirement to collect rock core for the pile foundation design. And then you'll notice the 3 CPTs in blue, and at the left-hand side in the west, you'll notice 2 CPTs right near one another. And the first one was abandoned at a shallow depth because we did encounter an obstruction, and so we moved over about 5 feet and performed a second CPT to refusal. Next slide. And so what you're seeing here is the stratigraphy that we developed along the proposed center line of the adjusted center line of Route 2, with west on the left, east on the right. And you'll notice just what we expected from the historical borings and the geology, that we have a variable bedrock surface with bedrock in gray that's shallower in the west and very deep in the east. The bedrock ranged from 30 feet below the ground surface to 158 feet below the ground surface. You'll notice variability in the layer thicknesses. We have the fill associated with the previous construction of US2. We have the in situ alluvium that we learned about in terms of the regional geology. And then you'll notice there are two types of clay. They're glacial lacustrine clay. The upper is a lower plasticity material that we determined the boundaries for based on the laboratory characterization of the SPT samples and kind of the trends in the CPT. And then the lower is a higher plasticity clay. And then we have the till in pink. And so the variability in the layer thickness was very important in our engineering analyses of the embankment, abutment, and MSE wall stability, bearing, and settlement, and specifically the pile design, down drag loading. Next slide, Steve. So as a way to kind of show you how CPT benefited this project and our analyses improved, what we're showing here is two separate undrained shear strength profiles. And so what you're seeing on the left is, and this is for at boring 110, which is that eastern abutment location, specifically for the clay, is our best guess design profile in yellow based on the vein shear data that we collected in two borings associated with that abutment. You can see the higher undrained shear strengths at those three data points in the upper left right-hand corner of this first plot, but it's not very clear to us how we would have incorporated those data. And so our original assumption was to have a constant undrained shear strength within that clay layer, even though we knew that it had a higher overconsolidation ratio and thus should have a higher strength. But ultimately what the CPT did for us was allow us in the right-hand image to better hone our undrained shear strength profile because we were able to use not only the correlated data from the NKT value for SU based on the comparison with both the field vein and the laboratory strength data from Shelby tubes. And we were able to look at the trends that the CPT provided us once it was correlated to better determine a design profile where we had a higher strength in the shallower clay layers, and then we had a little bit higher strength deeper down that tracked well with both the field vein data and the CPT data. So this is actually quite important because our original analyses for embankment stability yielded very low factors of safety, and the alternatives that we were starting to consider included things like rammed aggregate piers, wick drains, and preloading and surcharge loading, as well as the use of lightweight fill and potentially timber piles as a way to stabilize these embankments that were getting factors of safety of definitely less than 1.3. Next slide, Steve. And so to revisit the image that Steve presented a little bit earlier, which shows the plan of each of these features, embankments, abutments, and the MSE walls, we were able to use our improved undrained shear strength profile to evaluate the stability of the MSE walls and the embankments, and to also hone in on the amount of lightweight fill that we were going to be recommending in order to meet the global stability and the bearing requirements for these features. And so it might be a little bit challenging to see, but for these embankments that we were working with, we were able to propose conventional fill in the west as a cost savings, and we were able to use lightweight fill and conventional fill rather than just lightweight fill in the embankments to the east. With respect to the MSE walls, we were able to use these data to have conventional fill in the MSE wall in the east and lightweight fill for the MSE wall in the west. So rather than come up with a much more expensive recommendation for the use of wick drains or some sort of rigid inclusions, which ended up being impossible anyway because the stability, potential unstable slope or lower factor of safety, instabilities were deeper and would have been very costly to try to mitigate rather than the removal of excess load by the use of lightweight fill. And the higher undrained shear strengths closer in the surface that we developed from the CPT profile really made it possible for us to hone in on limiting the quantity of lightweight fill in order to help us achieve a factor of safety. Next slide, Steve. So I'll start off with this slide and then Steve will finish. So from the standpoint of us as an engineer, for the engineers on this project, the CPT-derived engineering properties were integral to the improved evaluation of the design. We had more detailed undrained shear strength to evaluate pile down drag forces as well as lateral responsive drivability. And it's important to note for this project because particularly for the eastern abutment, we had 150, the bedrock was very deep, and we also had 94 feet of this soft clay material, less than 1,000 PSF undrained shear strength. So we had a lot of down drag loading, and so we had to be very clear to understand the down drag forces in the design of the piles themselves and how to adequately size the piles. We're able to use the shear wave velocity measurements from the seismic piezo cone to improve our seismic site class. Typically, the SPT end values are weight of hammer, weight of rod, which yields a seismic site class of E for this site, but because we had the shear wave velocity, we were able to improve this to class D. Steve, do you want to finish up?
Sure, thanks, Melissa. So as far as the benefit from the owner's perspective, this bullet point touches on the AASHTO requirements for resistance factors that were used in design. So per the latest AASHTO spec, the resistance factors are no longer contingent on whether a slope supports or contains a structure, but they're based on the degree to which the geotech parameters and the stratigraphy are considered to be well defined. So this article that's referenced, it states that where the geotech parameters and subgrade stratigraphy are well defined, a resistance factor of 0.75 can be used, resulting in a factor of safety of 1.3 equivalent. So the spec also states that if a factor of safety or a resistance factor, sorry, of 0.65 should be used if the stratigraphy is highly variable or based on limited info. So for our purpose on this project, because we had the several CPTU profiles as part of our comprehensive investigation, we were able to direct the design team to use the higher resistance factor of 0.75 when looking at the stability of the MSE walls, as well as the embankments. And what that boils down to is the cost savings. So in summary, the cost savings that we saw as a result of both the lack of an additional seismic analysis and incorporating the CPT testing into our phase 1 subsurface investigation, both resulting in a less conservative design that would have been necessitated by not involving the CPT testing or the lower resistance factor, and ultimately avoiding the higher construction costs associated with that. So on to our final slide, some of the lessons learned with the CPT testing. Melissa, I'll let you jump in here.
Yeah, great. Right, so as I mentioned before, one of our CPTs, and in fact, several of them, we encountered obstructions and refusal. And so we had to terminate these because of shallow obstructions, because of, we later found out from nearby borings, these were likely boulders, as expected from the geology in the area. And so it's important, one of the lessons learned is that offset and refusal might be avoided if, when you're using a conventional drill rig, if you use that rig to then core through the obstruction and then continue the CPT below that. However, that may increase the time and the cost for both the CPT and the boring contractors. And also the refusal is unknown unless there's supplemental borings about whether or not it's till or bedrock. In the Northeast, some of our tills are quite strong. And so there is no replacement for identifying the bedrock surface, except, borings are the best way to still do that. In terms of site-specific validation and correlation, we still needed the conventional borings for the SPT samples for classification, vein shear for correlation, and also the Shelby tubes. But we were able to get quite a bit of data for the correlations from just a few Shelby tubes and the vein shears, and so we consider that a success. But we did find that it was important because typical correlation factors from the literature are a good start. For instance, NKT recommendations are typically 8 to 18, but that's a very wide range, and we were able to narrow that down when we had site-specific data to correlate the CPT with. And then lastly, there is still a need for attention when other tests are specified. For instance, we specified a several dissipation tests to determine permeability and coefficient of consolidation. Typically, it's desired to run these tests in 90% dissipation, but practice, in order to reduce cost and time, typically an operator will go to 50 to 60% of consolidation based on an assumed water table. However, the short durations of the tests from this investigation yielded inconclusive data, and we used the data gathered from lab tests instead. And to kind of go along with this, for some CPTs at other sites where we know we have artesian conditions, if you know there are artesian conditions, it's very hard to assume a water table to get to 50 or 60% consolidation. And so it ends up being inaccurate. And so recommendation for, and something that we've done ourselves in our geotech practice, is to run the dissipation test longer, but you have to plan for the time and the cost associated with the duration increase to get better dissipation test data. Next slide. And with that, Steve and I would like to thank you for listening to our presentation, and we're welcome to answer questions from you when the time comes.
Thanks, Steve and Melissa, for a very interesting presentation. For those of you that know me, you know I'm a very strong proponent of CPT. And no, I did not have any influence on the content, but to see there the benefits of CPT obviously is something that hopefully many will take away from this presentation. And also that with additional soil investigations, you can increase that resistance factor and therefore optimize your design. The question